Today we're going to look at two graphing stories. For student outcomes, you will interpret the meaning of the point of intersection of two graphs, and you'll use tools to find the coordinates of that intersection point. We're going to do this front page tomorrow in class, but for now, we are going to look at the second page. Number 1, read the following story carefully and answer the questions that follow. So, it says, suppose two cars are traveling north along a road. Car 1 travels at a constant speed of 50 miles an hour for 2 hours. Speeds up, drives a constant speed of 100 miles per hour for the next hour. The car breaks down and the driver has to stop and work on it for 2 hours. When he gets it running again, he continues driving recklessly at the constant speed of 100 miles an hour. Car 2, on the other hand, he starts at the same time as Car 1, but starts 100 miles further north and travels at a constant speed of 25 miles per hour throughout the trip. Graph the distance versus time graphs for the cars. Start with time 0 and measure time in hours. So, time in hours and distance from the starting point of the car. We had the start of the labels already, so we just finished them up there for you. I'm actually going to start with car 2 here because that's an easier one to graph in my opinion. So for car 2, there's just less going on. He starts 100 miles further north and travels at a constant speed of 25 miles per hour throughout the trip. So he starts 100 miles north, so that's where I'm going to put my first stop. And he drives 25 miles an hour. So notice my axes labels go up by 50s. So he goes 50 miles in 2 hours. 50 miles in 2 hours. 50 miles in 2 hours. So I just have that straight line in orange there. And then car 1 is a different story. He does start at time 0. He goes, or at distance from car 1 at 0. He starts out going 50 miles an hour for 2 hours. So he goes 50 miles in an hour and another 50 in an hour. From there, he speeds up. He goes 100 miles an hour for the next hour. So he goes 100 miles in 1 hour. Then his car breaks down because he's driving too fast and he has to sit there for 2 hours. So he's not going anywhere. He's just sitting for 2 hours. And then after he fixes his car, he again goes 100 miles in 1 hour. And ignore the dotted line for now. We'll get to that later. Approximately when do the cars pass each other? How do you know? They pass each other here, here, and here, which are at 2.5 hours, 4 hours, and 5.5 hours. How do I know that? The cars pass each other where the two graphs intersect. Tell the entire story of the graph from the point of view of car 2, so from our orange line. In other words, what does the driver of car 2 see along the way? Well, he's driving for 2.5 hours, but after 2.5 hours, he sees car 1 pass him, right there. After 4 hours, he passes car 1, because he sees car 1 on the side of the road because it's broken down. So see right there? So he sees car 1 broken down on the side of the road. But then after 5.5 hours, that car passed him again. That's right here. Okay, we just have part D and part E left. Part D says, create linear equations representing each car's distance in terms of time, hours. Note that you'll need 4 equations for car 1 and only 1 equation for car 2. Use these equations to find the exact coordinates of when the cars meet. For part D, notice it is listed as optional. What we're going to do is we're just going to find the equation for car 2 for practice, and that's it. So for car 2, if I look back up, car 2 is my orange graph. On the y-axis, it hits the y-axis at a value of 0, so that's our y-intercept. And my slope, don't think of it as 25 miles an hour. That's going to mess you up. Look back at your graph to find the slope. The slope is going to be up 1, right 2. That's a slope of 1/2. So your equation is y equals 100 plus 1/2 x. 100 because that's where you started, and the slope was a 1/2. And then letter E, suppose that car 1 travels at a constant speed of 25 miles an hour the entire time. Use a dotted line and graph the line on the grid above. Would the cars ever pass each other? What is the linear equation for car 1 in this case? So going back up to our graph, instead of having this graph as our car 1, we now have the dotted line graph. It starts at time 0 just like I started before, but it said it had a constant speed of 25 miles an hour. So it, according to our axes labels, in order to go up 1, that's 50 miles, it takes a distance of 2 hours. So I'm going up 1, right 2. With those dots, I draw my dotted graph. And the second part of the question asks, will the dotted graph ever intersect with the orange graph? Even if I were to continue this graph further along, it would never intersect. And the reason is because the slopes are exactly equal. Okay, they're both 25 miles an hour, or a 1/2 x. Since this one started at time equals 0, notice I don't have a y-intercept for this graph. Okay, it's just equal to 0. Therefore, my equation is just y equals 1/2 x, no intercepts, so we can stop right there for that particular equation. And tomorrow in class, we'll do the first page.